हेलो एवरीवन। आज हम स्टार्ट करते हैं मॉडल इवोल्यूशन मैट्रिसेस फॉर मशीन लर्निंग दैट एवरीवन शुड नो। Evaluating a model is a core part of a building an effective machine learning model. There are several evaluation metrics in machine learning like confusion metrics, cross-validation metrics, AUC-ROC curve, etc. Different evaluation metrics for logistic regression are used for different kind of a problem. Mainly अगर आपको पता है तो हमारी दो टाइप्स की प्रॉब्लम रहते हैं। एक रहती है हमारी क्लासिफिकेशन की, दूसरी है रिग्रेशन की। अगर हम रिग्रेशन में भी लॉजिस्टिक रिग्रेशन की बात करते हैं तो उसको इवेल्यूएट करने की कितनी रीत रहती है जो हम यहाँ पे आज पढ़ेंगे। पहले हम इंट्रोडक्शन से स्टार्ट करते हैं। द आइडिया ऑफ बिल्डिंग मशीन लर्निंग मॉडल्स वर्क्स ऑन अ कंस्ट्रक्टिव फीडबैक प्रिंसिपल। यू बिल्ड अ मॉडल, गेट फीडबैक फ्रॉम मैट्रिक्स, मेक इम्प्रूवमेंट्स एंड कंटिन्यू until you achieve a desirable accuracy. Evaluation metrics explain the performance of a model. An important aspect of a evaluation metrics is their capability to discriminate among model results. I have been I have seen plenty of analysis and aspiring data scientists not even bothering to check how robust their model is. Once they are finished building a model, they hurriedly map a predicted values on an unseen data. This is an incorrect approach. Basically अभी क्या है, अभी जो मशीन लर्निंग इंजीनियर्स रहते हैं मॉडल तो एक बार बिल्ड कर देते हैं लेकिन फिर उसकी एक्यूरेसी पे ये लोग फोकस नहीं करते। अगर मान लेते हैं कि उसकी एक्यूरेसी 70% ही आती है तो उसको कैसे इम्प्रूव करें इसके बारे में अभी जो एस्पायरिंग डेटा साइंटिस्ट है वो लोग नहीं सोच रहे। तो अभी ये गुड अप्रोच नहीं है। तो उसको ये वाले इश्यू को रेक्टिफाई करने के लिए ही ये हमने सोचा है कि इवैल्यूएशन मैट्रिक्स पे ज़्यादा फोकस करेंगे। Simply building a predictive model is not a your motive. It's about creating and selecting a model which gives the accuracy on out of sample data. Hence, it is crucial to check the accuracy of your model prior to computing predictive values. In our industry, we consider different kind of matrices to evaluate our model. अभी यहाँ पे हम लोग 11 मैट्रिसेस के बारे में बात करते हैं तो उसके कंटेंट्स पहले देख लेते हैं। कन्फ्यूजन मैट्रिक्स, which are the kind of evaluation metrics that we should focus on. Confusion matrix, F1 score, gain and lift charts, Kolmogorov-Smirnov chart, a UC-ROC, log loss, Gini coefficient, discordant ratio, root mean squared error, cross validation. Warming up types of predictive models. When we talk about predictive models, we are talking either about a regression model or a classification model. The evaluation metrics used in each of these models are different. In classification problem, we have two types of algorithm. Dependent on the kind of output, it creates class output and probability output. What is class output? Algorithms like SVM and KNN creates a class output. For instance, in a binary classification problem, the output will be 0 or 1. However, today we have algorithms which can convert these outputs to probability, but these algorithms are not well accepted by the statistics community. The second is probability output. Algorithms are like logistic algorithm, random forest, gradient boosting, AdaBoost, etc. give probability outputs. Converting probability outputs to class output is just a matter of creating a threshold probability. In regression problem, we do not have such inconsistency in output. The output is always continuous in nature and requires no further treatment. अभी हम लोग एक एग्जांपल रहते हैं कि एक क्लासिफिकेशन मॉडल है। I have used my prediction for the problem BCA challenge on Kaggle. The solution of the problem is out of the scope of our discussion here. However, the final prediction on the training set have been used for this article. The prediction made for this problem were probability outputs which have been converted to class outputs, assuming a threshold of 0.5. Confusion matrix. A confusion matrix is an Anchors and matrix where n is the number of classes being predicted. अभी हम लोग फर्स्ट जो है हमारा उस पे चलते हैं, इवोल्यूशन मैट्रिक्स विच इज़ कन्फ्यूजन मैट्रिक्स। इसमें एक मैट्रिक्स लिया है हमने एन क्रॉस एन, जिसमें एन है होगा हमारा नंबर ऑफ क्लासेस बीन प्रिडिक्टेड। फॉर द प्रॉब्लम इन हैंड वी हैव एन इक्वल्स टू 2, अभी हमारे पास दो क्लासेस है, hence we got 2 cross 2 matrix. Here are a few definitions you need to remember for a confusion matrix: accuracy, positive predictive value or a precision, negative predictive value, sensitivity or a recall or a specificity. अभी एक्यूरेसी की बात करते हैं। द प्रॉब्लम ऑफ द टोटल नंबर ऑफ प्रिडिक्शंस दैट वर करेक्ट। अगर हम लोग बात करते हैं कि एक्यूरेसी की, हमारे पास एक एल्गोरिथम है जिसमें हमें 10 चीज़ों का प्रिडिक्शन करना है कि 10 चीज़ों की वैल्यू क्या है। उसमें से एक्यूरेसी कैसे फाइंड करनी है? द प्रोपोर्शन ऑफ द टोटल नंबर ऑफ प्रिडिक्शन दैट वर करेक्ट, उसमें से 60% मतलब मान लेते हैं कि 10 है, उसमें से हमारे 6 वैल्यूज है जो सच है, तो उसकी एक्यूरेसी क्या हुई? इसको हम इजी में लेते हैं। हमारे पास 100 है, 100 थिंग्स है, उसमें से 60 थिंग्स हमारी सही है, तो हमारी एक्यूरेसी होती है 60%। उसको उस हिसाब से हम एक्यूरेसी को लेके चलना है। दूसरा है पॉजिटिव प्रिडिक्टिव वैल्यू और प्रिसिजन, द प्रोपोर्शन ऑफ अ पॉजिटिव केसेस दैट वर करेक्टली आइडेंटिफाइड। दूसरा है नेगेटिव प्रिडिक्टिव वैल्यू, द प्रोपोर्शन ऑफ अ नेगेटिव केसेस दैट वर करेक्टली आइडेंटिफाइड। नेक्स्ट है रिकॉल, द प्रोपोर्शन ऑफ एक्चुअल पॉजिटिव केसेस which are correctly identified. And specificity, the proportion of actual negative cases which are correctly identified. अगर अगर हम लोग प्रिसिजन की बात करते हैं तो क्या है? प्रोपोर्शन ऑफ पॉजिटिव केसेस दैट वेर करेक्टली आइडेंटिफाइड। अगर हम एक बॉक्स लेते हैं जिसमें 10 हमारे रेड बॉल्स है और 10 ब्लू बॉल्स है, सो प्रिसिजन क्या होगा कि अगर मैं ऐसा प्रिडिक्ट करती हूँ कि इसमें 6 रेड बॉल है और 6 रेड बॉल है और 14 ब्लू बॉल है, तो हमारा सही कितना हुआ? सही होता है हमारा 10 + 6 विच आर 10 ब्लू बॉल्स है हमारा राइट, और 6 जो हमने हमारे रेड बॉल में काउंट किया वो भी हमारा राइट है। तो इतना हमारा प्रिसिशन होता है क्योंकि हमने 20 में से 16 जो चीज़ है वो हमने राइटली पॉजिटिवली उसको आइडेंटिफाई किया है। नेगेटिव क्या है कि द प्रोपोर्शन ऑफ अ नेगेटिव केसेस दैट वर करेक्टली आइडेंटिफाइड। नेक्स्ट इज रिकॉल, द प्रोपोर्शन ऑफ एक्चुअल पॉजिटिव केसेस विच आर करेक्टली आइडेंटिफाइड। और यहाँ पे हमने कन्फ्यूजन मैट्रिक्स में दिया गया है क्या है कि मॉडल है जिसकी पॉजिटिव वैल्यू है नेगेटिव है। टारगेट क्या है हमारा? पॉजिटिव नेगेटिव। अगर जो हमारे मॉडल ने पॉजिटिवली रिएक्ट किया है और हमारा टारगेट भी पॉजिटिव है तो उसकी वैल्यू ये रहेगी। टारगेट हमारा नेगेटिव है लेकिन हमारे मॉडल ने पॉजिटिवली रिएक्ट किया तो उसकी वैल्यू बी होगी। अगर नेक्स्ट ले देते, टारगेट हमारा पॉजिटिव है लेकिन हमारे मॉडल ने नेगेटिवली रिएक्ट किया है तो उसकी वैल्यू सी रहेगी। हमारा टारगेट नेगेटिव है और उस हमारे मॉडल ने भी नेगेटिव रिएक्ट किया है तो उसकी वैल्यू डी रहेगी। तो हमारी सेंसिटिविटी बनती है A/A+C। नेगेटिविटी के रिगार्डिंग स्पेसिफिसिटी बनती है D/B+D। हमारी पॉजिटिव प्रिडिक्टेड वैल्यू रहती है A/A+B। हमारी नेगेटिव प्रिडिक्टेड वैल्यू रहती है D/C+D। तो हमारी एक्यूरेसी बनेगी A+D/A+B+C+D। The accuracy of the problem in hand comes out of 88%. As you can see from the above two tables, the positive predictive value is high but negative predictor value is quite low. Same holds for the sensitivity and specificity. This is primarily driven by the threshold value we have chosen. If we deserve, if we decrease our threshold value, the two pairs of slightly different numbers will come closer. In general, we have concern with one of the above defined metrics. For instance, in a pharmaceutical company, they will be more concerned with minimal wrong positive diagnosis. Hence, they will be more concerned about high specificity. On the other hand, an attrition model will be more concerned with sensitivity. Confusion metrics are generally used only with the class output models. On the other hand, an attrition model will be more concerned with the sensitivity. यहाँ पे हमने सेंसिटिविटी देखी है कि हमारी पॉजिटिव वैल्यू है डिवाइडेड बाय पॉजिटिव प्लस नेगेटिव जो हमारी सेंसिटिविटी रहती है मेनली हमारी जो कंपनीज रहती है अगर हम हॉस्पिटल की बात करते हैं तो ये लोग सेंसिटिविटी पे ज़्यादा फोकस करते हैं क्योंकि कितना उसने पॉजिटिवली रिएक्ट किया है डिवाइडेड बाय कितना उसने पॉजिटिव प्लस नेगेटिव रिएक्ट किया है। नेक्स्ट आता है F1 स्कोर। In the last section, we discussed precision and recall for the classification problem and, and also highlighted the importance of choosing precision recall basis over use case. What if, for use case, we are trying to get the best precision and recall at the same time? F1 score is the harmonic mean of precision and recall values for a classification problem. The formula for F1 score is as follows. F1 equals to recall minus 1 plus precision minus 1 divided by 2 whole inverse equals to 2 cross precision star recall divided by precision plus recall. Now an obvious question that comes to my mind is why are taking a harmonic mean and not an arithmetic mean? This is because HM punishes extreme value more. Let us understand this with an example. We have a binary classification model with the following result. हम लोग एक बाइनरी क्लासिफिकेशन प्रॉब्लम ले रहे हैं जिसमें हमारा प्रिसिशन है 0 एंड रिकॉल है 1. Here if we take the arithmetic mean we get 0.5. It is clear that the above results comes from a dumb classifier which just ignores the input and just on predicts one of the classes as output. Now, if we were to take HM, we will get 0, which is accurate as this model is useless for the purpose. यहाँ पे क्या हुआ है हम लोग प्रिसिशन 0 लिया रिकॉल 1 लिया है तो अगर हम लोग ये वाले फॉर्मूला में उसकी वैल्यू डालते हैं 2 क्रॉस 0 डिवाइडेड बाय 0 प्लस 1 सो हमारी इवेंचुअली F1 स्कोर वुड बी 0. सो अगर हमारा F1 स्कोर 0 रहता है तो ये मॉडल की कोई वैल्यू है ही नहीं मतलब ये यूजलेस मॉडल है ऐसा इन लोगों का कहना है क्योंकि अभी F1 स्कोर उसका 0 रहेगा था ऐसे वैल्यू F1 स्कोर वाला मॉडल हम लोग नेक्स्ट प्रिडिक्शन में यूज़ करेंगे तो उसकी वैल्यू डेफिनेटली विल नॉट गिव अ प्रॉपर आउटपुट. दैट्स वाई. This seems simple. There are situations, however, for which a data scientist would like to give a percentage more importance weight to either precision or recall, altering the above expression a bit such that we can include an adjustable parameter beta for this purpose. We get f beta equals to 1 plus beta square star precision recall divided by beta square precision plus recall. F beta measures the effectiveness of a model with respect to a user who attach beta times as much importance to recall as precision. हमारी ओरिजिनल फॉर्मूला थी प्रिसिशन स्टार रिकॉल डिवाइडेड बाय प्रिसिशन प्लस रिकॉल क्रॉस 2. यहाँ पे हम लोगों ने क्या किया है 2 है 2 का हम लोगों ने डिवाइड किया है 1 प्लस बीटा स्क्वायर. बाकी ये वाला जो था प्रिसिशन स्टार रिकॉल डिवाइडेड बाय प्रिसिशन प्लस रिकॉल यहाँ पे भी हमने प्रिसिशन में एक न्यू वेरिएबल ऐड किया है विच इज़ बीटा स्क्वायर. इसकी इसका पर्पस क्या है एफ बीटा मेजर्स द इफेक्टिवनेस ऑफ अ मॉडल विथ रिस्पेक्ट टू अ यूजर हु अटैचेस बीटा टाइम्स एज मच इम्पोर्टेंस टू रिकॉल एज प्रिसिशन. यहाँ पे बीटा स्क्वायर को ऐड करने से रिकॉल को भी इतना ही इम्पोर्टेंस मिलता है जितना हमको प्रिसिशन से मिलता है. सो इट विल इवेंचुअली इफ मेक अवर मॉडल मोर इफेक्टिव. नेक्स्ट आते हैं gain and lift charts. Gain and lift charts are mainly concerned to check the rank ordering of the probabilities. Here are the steps to build a lift or a gain chart. Calculate probability for each observation. Calculate probability for each observation. Rank the probabilities in decreasing order. Build decels with each group having almost 10% of the observation. Calculate the response rate at each decels for a good responders, bad for a non-responders, and total. You will get following table for which you need to plot gain और लिफ्ट कार्ड्स. यहाँ पे हम लोग देखते हैं लिफ्ट स्लैश गेन दिया हुआ है, कॉलम लेबल्स दिया हुआ है, रो लेबल्स दिया गया है, ग्रैंड टोटल दिया गया है, परसेंटेज राइट्स, परसेंटेज रॉन्ग्स, परसेंटेज पॉपुलेशन, कम परसेंटेज राइट, कम परसेंटेज पॉपुलेशन एंड लिफ्ट. This is a very informative table. Cumulative gain chart is the graph between cumulative percentage right and cumulative percentage population. For the case in hand, here is the graph. There is a very informative table. सो क्यूमुलेटिव गेन चार्ट यहाँ पे दिया गया है जिसमें हम लोग पहले देखेंगे तो एक्स एक्सिस पे परसेंटेज ऑफ पॉपुलेशन दी गई है और वाई एक्सिस पे परसेंटेज ऑफ रिस्पॉन्डर्स दिया गया है. यहाँ पे दो मॉडल दिया गया, वन इज रैंडम, द वन इज अवर मॉडल. दिस ग्राफ टेल्स हाउ वेल द योर मॉडल segregated responders from non-responders. For example, the first decile, however, has 10% of the population, has 14% of the responders. This means we have a 140% lift at first decile. What is the maximum lift we could have reached in the first decile? From the first table of this article, we know that the total number of responders are 3850. Also, the first decile will contain 543 observation. Hence, the maximum lifts as at first decile could have been 543 divided by 3850 equals to 14.1%. Hence, we are quite close to perform to perfection with this model. Let's now plot the lift curve. Lift curve is the plot between total lift and percentage population. Note that for a random model, this always stays flat at 100%. Here is a plot for the case in hand. लिफ्ट चार्ट. यहाँ पे चार्ट में डिसेल दिया गया है एक्स एक्सिस पर और वाई एक्सिस पर लिफ्ट दिया गया हुआ है. रैंडम का परफॉर्मेंस 100% है और हमारे मॉडल का परफॉर्मेंस 140% से स्टार्ट लेके 100 तक होता है. यू कैन ऑल्सो प्लॉट ए डिसाइल वाइज लिफ्ट विथ डिसाइल नंबर, लिफ्ट एट डिसाइल चार्ट. यहाँ पे भी मॉडल का परफॉर्मेंस जो रैंडम है उसका परफॉर्मेंस 100% दिख रहा है और हमारे लिफ्ट एट डिसाइल का 140% से लेके 0% तक जाता है. What does this graph tell you? It tells you that our model does well till 7th decile, post which every decile will be switched towards non-responders. Any model with lift at decile above percent till minimum 3rd decile and maximum 7th decile is good model. Else you might consider oversampling first. यहाँ पे आप देखोगे तो 7 तक हमारा बेस्ट परफॉर्मेंस हम बोल सकते हैं कि 140 से लेकर 100 तक हुआ है, लेकिन 7 के बाद उसका परफॉर्मेंस डाउन जाता है. जो सैम्पलिंग लिया है वो वी माइट कंसिडर ओवर सैम्पलिंग फर्स्ट. Lift gain charts are widely used in campaign targeting problems. This tells us till which decile we can target customer for a specific campaign. Also, it tells you how much response to expect from the new target base. नेक्स्ट आता है कोलोमोगोरोव स्मिनो चार्ट, KS, or it is also called as a KS. It measures the performance of a classification model. More accurately, KS is a measure of a degrees of a separation between the positive and a negative distribution. The KS is 100 if the scores partition the population into two separate groups, in which one group contains all the positives and the other all are negatives. On the other hand, if the model cannot differentiate between positive and negative, then it is as if the model selects cases randomly from the population. The KS would be 0. In most classification models, the KS will fall between 0 to 100, and that The higher the value, the better the model is at separating the positive from negative cases. For the case in hand, following is the table. We can plot also the percentage cumulative good and bad to see the maximum separation. Here, red line shows the bad, blue line shows the good, and the KS value is 82%. Max separation between good and bad at the one particular time. The metrics covered till here are mostly used in the classification problem. Till here, we learn about confusion matrix, lift, gain chart, and a KN chart. Let's proceed and learn few more important matrices. Next is area under the curve. See curve. This is again one of the popular matrices used in the industry. The biggest advantage of using ROC curve is that it is independent of a change in the proportion of a responder. Let's first try to understand what is ROC curve. If we look at the confusion matrix below, we observe that for a probabilistic model we get different values for each matrix. Confusion matrix. Here we have model positive, negative, target will be positive and negative as well. A, B, C, D, sensitivity, specificity, prediction, positive prediction, negative prediction, and accuracy. Hence, for each sensitivity, we get a different specificity. The two vary as follows: specificity, true negative rate, and true पॉजिटिव रेट सेंसिटिविटी. यहाँ पे हमने देखा है कि सेंसिटिविटी डिपेंड्स करती है ए डिवाइडेड बाई ए प्लस सी. तो एंड हमारी हमारी जो स्पेसिफिसिटी है वो डिपेंड करती है डी डिवाइडेड बाई बी प्लस टी. Hence, for each sensitivity, we got a different specificity. The two vary values are as follows. The ROC curve is the plot between sensitivity and 1 minus specificity. 1 minus specificity is also known as a false positive rate and sensitivity is also known as true positive rate. Following is the ROC curve for the case in hand. यहाँ पे आरओसी कर्व में हम देख सकते हैं कि एक्स एक्सिस पर 1 माइनस स्पेसिफिसिटी लिया गया है और वाई एक्सिस पर सेंसिटिविटी लिया गया है. उसका हमारा रैंडम जो चार्ट रहेगा वो 0 से 100 तक जाता है. लेकिन हमारा जो मॉडल का परफॉर्मेंस रहता है वो इनिशियल लेवल पे 80 टू 100 रहता है. 80 टू 100 रहता है और लाइक इनिशियल लेवल पर ये बढ़ता रहता है और फिर वो जाके 100 तक. After 40 or hours, after 20 or 30% here in axis, it will go in straight to 100%. Let's take an example of a threshold. Point 5. Refer to confusion matrix. Here is the confusion matrix. Target 1, 0. It is equals to, यहाँ पे हमें टारगेट दिया गया है 3834 16 3850 99%. एंड यहाँ पे 0 है जिसका रहता है 639 951 1500 एंड 40%. मतलब हमारे पास दो क्लास है 1 एंड द सेकंड वन इज़ 2. यहाँ पे उसका परसेंटेज हमने लिया हुआ है. एज यू कैन सी द सेंसिटिविटी एट दिस थ्रेशोल्ड इज 99% and 1 minus specificity is 60%. This coordinate becomes on point in ROC curve. To bring this curve down to a single number, we find the area under this curve, which is AUC curve. Note that the area of entire square is 1 cross 1 equals to 1. Hence, AUC itself is the ratio under the curve and the total area. For the case in hand, we get AUC-ROC as 96.4%. These are some thumb rules. 90 minus 1 equals to excellent. 80 to 90 it's a good. 70 to 80 it's a fair. 60 to 70 poor. 50 to 60 fail. We see that we fall under the excellent band for the current model, but this might simply be overfitting. In such cases, it becomes very important to in-time and out-time of validation. Point to remember, for a model which gives class as output will be represented as a single point in ROC plot. Such models cannot be compared with each other as the judgment needs to be taken on a single matrix and not using multiple metrics. For instance, model with parameters zero point 0.2 and zero point 0.8 and model with parameters zero point 0.8 and zero point 0.2 can be coming out of the same model. Hence, these metrics should not be directly compared. In case of probabilistic model, we were fortunate enough to get a single number which was AUC-ROC, but still we need to look at the entire curve to make conclusive decisions. It is also possible that one model performs better in some regions and other performs better in another. Advantages of using ROC curve. Why should you use ROC and not metrics like a lift curve? Lift is dependent on total response rate of the population. Hence, if the response rate of the population changes, the same model will give a different life chart. A solution to this concern can be true lift chart. ROC curve, on the other hand, is almost independent of the response rate. This is because it has the two axes coming out from a columnar calculation of the confusion matrix. The numerator and denominator of both x and y axes will change on similar scale in case of response rate shift. Log loss. AUC-ROC considers the predicted probabilities for determining our model's performance. However, there is an issue with AUC-ROC. It also takes into account the order of probabilistic and hence it does not take into account the model's capability to predict higher probability for sample more likely to be positive. In that case, we could use we could use the log loss, which is nothing but the negative average of the logs corrected predicted probabilities for each instance. नेक्स्ट हमारा जो log loss, यहाँ पे हमने जो AUC-ROC था वो predicted probability for determining our model's performance. There is an issue, some issues are there in AUC-ROC. It only takes account of a probabilistic and hence it does not take into the account the model's capability to predict higher probability for samples more likely to be positive. इसलिए हम लोग यहाँ पे log loss का यूज़ कर रहे हैं. इसकी यहाँ पे फॉर्मूला दी गई है -1 divided by sigma I equals to 1 to n yi cross log p yi plus 1 minus yi dot log 1 minus p of yi. Here p of yy is predicted probability of a positive class. 1 minus p of yy is predicted probability of negative class. Yi equals to 1 for positive class and 0 for negative class. Let us calculate log loss for a few random values to get the list of above mathematical function. Log loss 1 0.1 equals to 2.3. यहाँ पे log loss की जो फॉर्मूला है यहाँ पे हम लोगों ने वैल्यूज़ ली हुई है. यहाँ पे दिखते तो ये वाली जो 1 एंड 0.1 वाली वैल्यूज़ यहाँ पे डालेंगे हम लोग तो हमें लॉग लॉस की ये वैल्यू 2.3 मिलेगी. अगर हम 1 और 0.5 को लेके चलते हैं तो 0.695 की वैल्यू मिलेगी. Log loss for 1 comma 0.9 then value will be 0.1. If we plot the relationship we will get a curve as follows. Log loss would be coming to 1. It's apparent from the general downward slope towards the right that the log loss gradually declines as the predicted probability improves. जो हमारा यहाँ पे दिखता है it's apparent from the gentle downward slope towards the right that the log loss gradually declines as the predicted probability improves. यहाँ पे जो हमारी प्रिडिक्शन रहता है उसकी प्रोबेबिलिटी जैसे ही इंक्रीज होती है हमारा जो लॉग लॉस रहता है जो लॉस है मतलब लॉस के जो वैल्यूज रहती है वो धीमे धीमे कम होती जाती है. So lower the log loss, better the model. However, there is no absolute measure on a good log loss. It is use case application dependent. Whereas the AUC computer with regards to binary classification with a varying decision threshold, log loss actually takes certainty of a classification into account. Next is Gini coefficient. Gini coefficient is sometimes used in a classification problems. Gini coefficient can be straight away derived from the AUC-ROC number. Gini is nothing but the ratio between area between the ROC curve and the diagonal line and the area of the above triangle. Following is the formula used. Gini equals to 2 cross AUC minus 1. Gini above 60% is a good model. For the case in hand, we get Gini as 92.70%. Gini coefficient is sometimes used in the classification. And Gini coefficient can be straight away derived from AUC-ROC number. यहाँ पे जो AUC वैल्यू है 2 क्रॉस AUC माइनस 1 है जो हमारे जीनी वैल्यू रहती है और उसकी वैल्यू 60% से ज़्यादा हो तो अच्छा मॉडल है और यहाँ पे हम लोग की वैल्यू मिल रही है जीनी की 92.7%. Concordant and discordant ratio. This is again one of the most important metrics for any classification prediction problem. To understand this, let's assume we have three students who have some likelihood to pass this year. Following are the our predictions. A A2 A 0.9, B zero point 0.5, C zero point 3. Now in this picture, if we were to fetch pairs of two from these students, how many pairs will we have? We will have three pairs A, B, B, C, C, A. Now after the year's end, we saw that A and C passed this year while B failed. Now we choose all the pairs where we will find our responder and other non-responder. How many such pairs do we have? We have two pairs AB and BC. Now for each of two pairs, the concordant pair is where the probability of responder were higher than non-responder, whereas discordant pair is where the vice versa holds true. In case both the probabilities were equal, we say it's a tie. Let's see what happens in our case. AB equals to concordant, BC equals to discordant. Hence, we have 50% of concordant cases in this example. Concordant ratio of more than 60% in considered to be good model. This matrix generally is not used when this is deciding how many customers to target. It is primarily used to access the model's predictive power. For decisions like how many to target are again taken by KS or Lipstadt. Next is root mean squared error. RMSE is most popular evaluation matrix used in the regression problem. It follows an assumption that errors are unbiased and follow a normal distribution. Here are the key points to be considered. RMSE. The power of square root empowers this matrix to show large number of deviations. The squared nature of this matrix helps to deliver more robust results which prevents cancelling the positive and negative error values. In other words, the metric amply displays the possible magnitude of an error term. It avoids the use of absolute error values, which is highly undesirable in mathematical calculation. When we have more samples, reconstructing the error distribution using RMSE is considered to be more reliable. RMSE is highly affected by outlier values, hence make sure you have removed outliers from your data set prior to using this metric. As compared to mean absolute error, RMSE gives higher weightage and punishes large errors. RMSE matrix is given by RMSE equals to root sigma I equals to 1 to n predicted I minus actual I whole square divided by n, where n is total number of observation. हमारे पास अगर अगर हम लोग एग्जांपल लेते हैं कि हमारे पास 100 केसेस है जिसमें से 100 केसेस है जिसका हमने प्रिडिक्टेड वैल्यू भी निकाला है और हमारा एक्चुअल आउटपुट भी है हमारे पास, तो हमें उसकी आरएमएस कैसे निकालनी है? तो प्रिडिक्टेड माइनस एक्चुअल होल स्क्वायर डिवाइडेड बाय 100 लेना है और उसका हमें पूरा सिग्मा निकाल देना। हमें पहले एक्चुअल एरर फाइंड करनी है कि हमारी प्रिडिक्टेड वैल्यू हमारे एक्चुअल वैल्यू से कितने दूर है और सारी 100 केसेस की हमें वैल्यूज़ निकाल देनी है और उसका समेशन ले लेना है और डिवाइडेड बाय में 100 कर देना है। फिर जो वैल्यू आएगा उसका हमें रूट लेना है, तो उसका हमें वैल्यू मिल जाएगा रूट मीन स्क्वायर एरर। नेक्स्ट आता है रूट मीन स्क्वायर लॉजिस्टिक एरर। In case of root mean square logistic error, we take the log of the predictions and actual values. So basically, what changes are the variance that we're measuring. RMLAC is usually used when we don't want to penalize the huge differences in the predicted and the actual value when both predicted and true values are huge number. Basically क्या है, what changes are the variance that we are measuring. RMLAC is usually used when we don't want to penalize huge difference. अगर हमें ह्यूज डिफरेंस पेनलाइज नहीं करना है उस टाइम पे हमें यूज़ करना है रूटमीन स्क्वायर की जो हमारी फॉर्मूला है 1/n सिग्मा आई इक्वल्स टू 1 to n वाई माइनस वाई बार आई होल स्क्वायर और रूट मीन स्क्वायर लॉग एरर के वैल्यू है सेम है हमारा लेकिन यहाँ पे वैल्यू जो चेंज आया है वो है लॉग ऑफ पी आई प्लस वन माइनस लॉग ऑफ ई आई प्लस वन होल स्क्वायर यहाँ पे जो वैल्यूज़ है उसमें जो हमारी फर्स्ट वैल्यू है वाई है आई वो हमारी एक्चुअल वैल्यू है और यहाँ पे लॉग ए आई प्लस वन हमारी एक्चुअल वैल्यू है फिर इस यहाँ पे वाई आई बार है जो हमारी प्रेडिक्टेड वैल्यू है और यहाँ पे लॉग पी आई प्लस वन है जो हमारी प्रेडिक्टेड वैल्यू है इफ बोथ प्रेडिक्टेड एंड एक्चुअल वैल्यूज आर स्मॉल देन RMSE and RMLSE are same. If either predicted or the actual value is big, then RMSE would be greater than RMSLE. If both predicted and actual values are big, then RMSE would be greater than RMSLE. So at that time, RMSLE becomes almost negligible. Next is our R square or adjusted R square. We learn that when the RMSE decreases, the model's performance will improve. But these values alone are not intuitive. In the case of a classification problem, if the model has an accuracy of zero point 0.8, we could gauge how good our model is against a random model, which has an accuracy of zero point 0.5. So the random model can be treated as a benchmark. But when we talk about the RMSE matrix, we do not have a benchmark to compare. This is why we can use R square matrix. The formula for R square is as follows. R square equals to 1 minus MSE divided by 1 minus, which would be for model and divided by MSE baseline. Next is MSE model divided by MSE baseline. MSE model would be mean square error for the predictions against the actual value. MSE baseline would be mean square error of mean predictions against the actual value. यहाँ पे मीन प्रिडिक्शन रहता है और यहाँ पे सिर्फ प्रिडिक्शंस रहता है इन अदर वर्ड्स हाउ गुड अवर रिग्रेशन मॉडल एज कम्पेयर टू अ वेरी सिंपल मॉडल that just predicts the mean value of a target from the trained set of a prediction. Adjusted R square, a model performing equal to baseline would give R square as 0. Better the model, higher the R2 value. The best model with all correct predictions would give R squared as 1. However, in adding new features to the model, the R squared value either increase or remains the same. The R squared does not penalize for adding features that add no value to model. So, an improved version over the R squared is an adjusted R squared. The formula for R adjusted R square is given by R bar square equals to 1 minus R square whole n minus 1 divided by n minus k plus 1. K is the number of features, n equals to number of samples. As you can see, this matrix takes the number of features into the account. When we add more features, the term is denominator n minus k plus 1 decreases, so the whole expression increases. If R squared does not increase, that means the feature added is not valuable for our model. So overall, we subtract a great value from 1 and adjusted R2 in turn would decrease. Beyond this 11 metrics, there is another method to check the model performance. These 7 methods are statistically prominent in data science, but with arrival of a machine learning, we are now blessed with more robust model of model selections. Yes, I am talking about cross validation. Though cross validation it's not a really an evaluation metric which is used openly to communicate model accuracy, but the result of a cross validation provides good enough intuitive result to generalize the performance of a model. Let's now understand cross validation. Cross validation. Let's first understand the importance of a cross validation due to busy schedules. These days, I don't get much time to participate in data science competition, but previously I have participated, and this is something like TFI competition where there of my solution and score. Some files which I have submitted. You will notice that the third entry, which has the first public score, turned to be the best model on private ranking. There were more than 20 models about the submission, but I will choose submission all CSV file as my final entry. Overfitting is nothing but when your model become highly complex that it start capturing noise also. The noise adds no value to model, but only inaccuracy. In the following section, I will discuss how you can know if a solution is overfitted or not. The concept comes into the picture is cross-validation. Cross-validation is one of the most important concepts for data modeling. It simply says try to leave a sample on which you do not train the model and test the model on this sample before finalizing the model. Training population, intent validation and train. In above diagram shows how to validate a model with intent sample. We simply divide the population into two samples and build model on one sample. Rest of the population is used for intent validation. Could there be a negative side of the above approaches? I believe a negative side of this approach is that we lose a good amount of data from training the model. Hence, the model is very high bias, and this won't give best estimate for the coefficient. So, what's the next best option? What if we make 50-50 split of a training population and the train of on first 50 validation on a rest 50, then we train on another 50 test on first 50. This way we train the model on the entire population, have around 50% on one go. This reduces biases because of the sample selection to some extent, but gives a smaller sample to train and model on. This approach is known as a twofold cross validation. K-fold cross validation. Let's extrapolate the last example to k-fold from a two-fold cross validation. Now we will try to visualize how does a k-fold validation work. This is a seven-fold cross-validation. Here is what goes on behind scene. We divide the entire population into seven equal samples. Now we train models on a six samples and validate on one sample. Then at the second iteration, we train model with a different sample held as a validation. In seven iterations, we have basically built a model on each sample and held each of them as a validation. This is way to reduce the selection bias and reduce the variance in prediction power. Once we have all seven models, we take average of the error terms to find which of the model is best. How does this helps to find the best non-overfitted model? The K-fold cross-validation is widely used to check whether a model is an overfitted or not. If the performance metrics at each of the K times modeling are close to each other, and the mean of the matrix is highest in a Kaggle competition, you might really rely more on the cross validation score and not on a Kaggle public score. This way, you will be sure that the public score is not just by chance. अभी हमने देखा है कि फॉल भी अच्छा है क्योंकि उसमें हम लोग जो रहता है हमारा डेटा उसको डिवाइड करते हैं दो पार्ट में। पहले पहले पार्ट को हम लोग करते हैं टेस्ट, फिर ट्रेन करते हैं, फिर दूसरे पार्ट को ट्रेन करते हैं। उस हिसाब से हमारा जो वेरिएंस रहता है और जो बायस होती है वो कम आती है। तो ये भी कुछ अच्छा, काफ़ी अच्छा और यूज़ में आता है कि फॉल्ट क्रॉस वैलिडेशन। इस तरह से हमारा 12 इवेल्यूशन मैट्रिक्स यहाँ पे मैंने आपको बताया। अगर आपको कुछ भी डाउट हो तो कमेंट सेक्शन में बताइएगा, और आपको ये वीडियो अच्छा लगा हो तो प्लीज़ चैनल को लाइक शेयर एंड सब्सक्राइब कीजिएगा। थैंक यू।